So now we've got a rule, a nice rule. We were just looking at, what happens to the geometric series. And let me actually go back a slide. We were looking at the geometric series, and it's written, right here. And we wanted to know as what happens as n approaches infinity dependent on r. And what we realized is that if the absolute value of r was greater than 1, it diverged. Our sum diverged. If the absolute value of r was less than 1, it's going to converge. All right, so moving ahead. Just as a friendly reminder, we had that the sum of a geometric series, the sum from n equals 0 to infinity of a times r to the n was the limit, this is from before, as n approaches infinity of a times 1 plus r to the n plus 1 all over 1 minus r. And what we saw is that um, if r was less than 1, then my series is going to converge, and it converges to this value. Well, why does it converge to that value? Because we noticed is as n got hugely big, this value here approached 0. So this, as n approached infinity, provided the absolute value of r was less than 1, my value approached a times 1 plus 0 over 1 minus r, which we could simplify to just a over 1 minus r. And so that's what this value here, this value, that is what my infinite geometric series will converge to, provided that r is less than 1. And if it's greater than or equal to 1, then the series diverges. Well, how can we use that? Let's think about this. Is the following series convergent or divergent? What we need to do is we need to write this. Let's think about this in terms of a geometric series. So we could rewrite this then as, we want to get it to look like this, a times r to the n. It sort of is like that, but we've got this denominator. So we could rewrite this as the sum from k equals 0 to infinity of 2 times, well, it's 2 times 1 over negative 3 to the k. 1 over, because all I did is, in the numerator I've got the 1. That's just 1 to the k, which is just 1. And then, I expressed this as a fraction. Equals the same thing. But by writing it that way, it's quick to identify that r equals, well, that's our r value. R equals negative 1/3. And we can see that the absolute value of r, which is the absolute value of negative 1/3, is less than 1. Therefore, we know that this series is going to converge. And what will it converge to? Well, S sub n converges to, if you need a hint, look back a slide, converges to a over 1 minus r, a over 1 minus r, where our a value is 2. That's our a value here. And our r value is negative 1/3. So 1 minus negative 1/3. We get 2 over 4/3, which is 6 over 4, or 3 over 2. So just as soon as we identify this as a geometric series and then identify the r value, we can very quickly, using that formula we've developed, figure out what this infinite sum will approach, or what it will converge to. And it converges to a value of 3/2. In other words, as n gets huge, the sum of this will come to a finite value, that finite value being 3/2. What about this one? Well, same idea. We need to express, is it convergent or divergent? We need to express it as a times r to the n. This one's actually easier. We have n equals 0 to infinity. Well, my a value is just a 1. So I have 1. And then this 3/2, well, that 3/2, that's my r. So r equals 3/2. 3/2 is greater than 1, or the absolute value is greater than 1. Since that r value, the absolute value, is greater than 1, we know that my um, my geometric series here, we know that this must diverge. In other words, it doesn't approach a singular value. Now, hang on with this. You might be, why do we care if it converges? Why do we care if it diverges? For now, we're just trying to build a skill set. Like I said a couple times in these videos, we're building a skill set that we're going to apply to doing difficult integration in a little bit. So uh, this is sort of, in a way, just kind of an off topic, but we're gonna make it an on topic in the next couple sections. So we're building a skill set and looking at geometric series or any series and deciding whether they converge or diverge. Let's look at another one. It says, find the first 5 terms of the sequence of partial sums. Graph the sequence of partial sums. Does it appear that the series converges or diverges? If the series converges, find its sum. Well, there's a lot of questions, or a lot of sort of preamble here. I'm going to jump right to the fun stuff. What we can notice is that my starting value is 1. So my starting value, if we think about a geometric series, my starting value is A. So we've got a 1, so this is going to be 1. Now I'm making an assumption this is geometric. It is, but we'll show why. And then what do? Well, then we have -4/3, 16/9, 64, -64 27. So what's our multiplier here? To get to each subsequent term, what pattern are we seeing? Well, in each case, we're multiplying the previous term by, we're multiplying the previous term by -4/3. In other words, if I have 1 times -4/3, I get to -4/3. That's my second term. And if I multiply that value by -4/3, I get to positive 16/9, this value. And if I multiply that, you know where this is going, by -4/3, we get to -64 27, this term. So that r value, the multiplier, that's my r value. So this is times -4/3 to the n. So the question is, does it appear that the series converges or diverges? Well, even before we, look at the r value, these numbers are getting bigger and bigger and bigger. So the fact that they're getting bigger and bigger and bigger, to me, implies that it's going to diverge. But if we want to use our rule, we can say, well, our r value is -4/3, and the absolute value of that is greater than 1. Therefore, does it appear that the series converges or diverges? It clearly diverges because the absolute value of my r value is greater than 1. Okay, then it says, in this exercise, so what I'm doing is trying to look at a couple sample problems so that you have you get used to the book language and are familiar with some problems so that when you start to do them, you've had some experience seeing them. So in part A, it says, determine whether A sub n is convergent. So remember, A sub n is the nth term. So here's what A sub n is. And we say, well, the limit, we want to know if it is convergent. So we say the limit as n approaches infinity. So we want to see if it converges. We want to know what happens when n gets huge, of 3n minus 1 over 2n plus 1. Well, to evaluate that limit, we could use L'Hopital's rule, and it's 3 over 2. So that the nth term converges to 3 over 2. So a over n converges to 3 over 2. In other words, my infinite term, I'm adding 3 halves. Well, if I'm adding 3 halves on my infinite term, my infinite sum is going to continuously get bigger. In other words, I'm continuing to add amounts. So because a sub n doesn't equal 0, we know that the series must diverge. In other words, or put differently, here's one way of writing it. We could write it that S sub n diverges. And we are able to say that purely because the nth term doesn't equal 0. Okay, so now kind of going back to kind of geometric series and identifying what's going on. It says determine whether the given series converges or diverges. If the series converges, find the sum. So what we can notice is I could rewrite this as 1 over 11 minus 10 over 11 squared plus 10 squared over 11 cubed minus 10 cubed over 11 to the fourth plus dot 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 dot, which I could then rewrite to make this even more clear as 1 over 11. Let me time out here. There's a lot of patterns that you're going to have to start identifying. So there's a lot of number theory, essentially. So what's going on? Trying to identifying a pattern, seeing the pattern, and then summarizing the pattern with an equation. So what I'm going to do now is rewrite this as 1 over 11 minus 10 over 11 times 11 plus 10 squared over 11 times 11 squared plus 10 cubed over 11 times 11 cubed. And I wrote it like that just because my starting value is 1 over 11. So if we think about this, if we can fit it into a geometric series, I'm saying that the a value is 1 over 11. And are we multiplying it by a constant amount? Well, we've got negative 10 over 11, and then it grows. Then we're multiplying. Each time we're multiplying by negative 10 over 11. So in other words, I started with 1 over 11. My next term I multiply by negative 10 over 11, which gets me negative 10 over 11 squared. And then my next term, I'm going to multiply that by negative 10 over 11, which is going to get me to positive 100 over 11 cubed. And so I start, I'm following this sequence. So by identifying this pattern, I'm able to model this sequence, or model this series rather, as the sum from n equals 0 to infinity of a. Well, my starting value is 1 over 11 times r to the n, where r is negative 10 over 11 to the n. Right away, I know that it converges. I know that it converges because my r value, the absolute value, is less than 1. So my r value, absolute value, equals the absolute value of negative 10 over 11, less than 1. So I know that my infinite series will converge, and it's going to converge to a over 1 minus r. Remember, just going back a couple slides. Provided that r is less than 1, that's what it converges to. So moving back to where we were, our a value is 1 over 11, 1 minus my r value, so 1 minus 10 over 11, which is plus. So simplifying this, I get 1 over 11 over 21 over 11, just finding out what that denominator is, 21 over 11, and that equals 1 over 21. So my infinite geometric series converges to this value, 1 over 21. And I think we're done here. Actually, there's one more. So I'm going to stop this, and there's going to be one more video.